Hello everybody and welcome to Physics Fridays, a new series on the channel where each and every Friday I'm going to be answering a question that has been posted within my physics course. So today's question is, why doesn't the photoelectric effect contribute to scatter if a characteristic X-ray is released when the photoelectric effect occurs? Now this is a great question because we need to understand not only X-ray production but also X-ray interaction with matter. We produce X-rays, some of which are characteristic X-rays, and then when X-rays are attenuated via the photoelectric effect, we also produce a characteristic X-ray. Now, why doesn't that characteristic X-ray leave the patient at a different angle to the incident X-ray and cause signal on our detector? Well, hopefully by the end of this, we'll understand exactly why. So first, we need to understand where these interactions are occurring. Here's our X-ray tube, our collimator, and our patient with our X-ray detector at the bottom here. X-rays are produced here. We are accelerating electrons from our cathode to our anode, and X-rays are produced here, either characteristic X-rays or Bremsstrahlung X-rays. Those X-rays then head towards our patient, and they can interact with matter prior to hitting our X-ray detector. This is where the photoelectric effect occurs and produces that small characteristic X-ray. So our X-rays heading towards our patient can either be transmitted through the patient, uninterrupted, no deflection in their angle. They can be attenuated by the patient. This is where the photoelectric effect occurs. Or they can be scattered via Compton scatter or Rayleigh scatter. Now, why doesn't that characteristic X-ray that is produced in the photoelectric effect head out of this patient and hit our detector? Well, in order to understand this, we can look at characteristic radiation production at the anode as well as the photoelectric effect and see the subtle differences between the two that will show us why this doesn't occur. So let's start by looking at characteristic radiation. We can split characteristic radiation into three different steps. Now, this is occurring at the anode within our X-ray tube. We have an electron here that is accelerating towards our anode. Now we know our anode is made of tungsten, a large atom here, 74 protons within the nucleus. If the energy of this bombarding electron is higher than the binding energy of this K-shell electron, that K-shell electron will then be released from the tungsten atom, as well as our incident electron being deflected away. We've now created a space within our K-shell here. That vacant space in our K-shell will cause an L-shell electron to fill that space. Now we know L-shell electrons are from a higher energy state going into a lower energy state, and that loss of energy state results in the release of energy, and this release of energy is what's known as characteristic radiation. Now it's called characteristic radiation because each and every atom has a different characteristic energy that X-ray would be released. And that energy of that X-ray is the difference between the binding energies of our L-shell and our K-shell electrons. So it's the binding energy of these K-shell and L-shell electrons that determine the energy of this characteristic X-ray. Now, what causes binding energy to increase or decrease? Well, binding energy is proportional to the number of protons within that nucleus and inversely proportional to the distance that that electron is away from that nucleus. You can think of binding energy as the attractive force between the protons in the nucleus and that negatively charged electron. How tightly is that nucleus holding onto that electron? How much energy do we need to put into that system in order for that electron to be released? Now let's have a look at the photoelectric effect. And the first main difference that we can see here is that instead of an electron coming in towards our atom, we have an X-ray coming towards our atom. This could be a Bremsstrahlung X-ray, or it could be this characteristic X-ray that we've just produced at the anode. That X-ray will then interact with the K-shell electron within our atom. Now the second difference here, we can see we have a much smaller atom here. Here we're dealing with soft tissue. The average atomic number of our soft tissue is 7. It's not 74. It's 10-fold fewer. That X-ray then collides with this K-shell electron, and all of that energy of that X-ray is then deposited into that K-shell electron. That K-shell electron is ejected from the atom, and it's ejected at a kinetic energy that's equal to the energy of that X-ray minus the binding energy of that photoelectron. And it's that photoelectron there that causes dose to be deposited in our patient, a concept known as linear energy transfer. Again, now we've created a vacancy within our K-shell, and our L-shell will then drop into our K-shell and release a characteristic X-ray. So what have we created here in the photoelectric effect? Well, we've created an ion. We've got an atom with one fewer electrons than it's supposed to have. We've created a photoelectron, which is going to deposit dose to the patient, and we've created a characteristic X-ray. Now, why doesn't that characteristic X-ray head off towards our detector and contribute to noise within our image? Well, we know that the binding energy of this K-shell electron must be much, much lower than the binding energy of this tungsten atom here. Because our atomic number is so low, we don't have that many positively charged protons keeping that electron within its orbit. So the binding energy here I've got oxygen, the binding energy is 0.5 keV. When we're looking at the binding energy of the K-shell electron in tungsten, that's 69.5 keV. So our characteristic X-ray that heads out of a tungsten atom is in the range of 57 keV. The characteristic X-ray that is released in tissue is the difference between our K-shell electron and our L-shell electron, which is less than 0.4 keV. We've got a characteristic X-ray that's more than 10-fold less energy than the characteristic X-ray that we produced at the anode. So this is a really low energy characteristic X-ray, and the fate of that characteristic X-ray is attenuation by the very process that caused it to happen, attenuation by the process of photoelectric effect. This X-ray is almost certainly not going to leave the patient's tissue because it's going to interact with other atoms within the tissue and be attenuated. When we look at this equation, I'm not going to go into it in depth, but this is the probability that the photoelectric effect will occur. It's proportional to the density of the tissue, the atomic number of the tissue, and inversely proportional to the energy of the X-ray. Now we know that this characteristic X-ray energy is extremely low, so the probability of it incurring the photoelectric effect is extremely high. They're inversely proportional. So this characteristic X-ray will be attenuated before it even has a chance of reaching our detector. And if it manages to exit our patient, it wouldn't stand a chance against the aluminium that's within our anti-scatter grid, so it most certainly wouldn't reach the detector. Another important point to note here is that this X-ray coming in has enough energy to reach our detector. We're not dealing with Compton scatter here, we're dealing with the photoelectric effect. This X-ray is not deflected and leaving the patient. All of the energy here is transferred into that photoelectron. So hopefully you can see the subtle differences between characteristic X-ray production at the anode and the photoelectric effect that happens within the patient. And this characteristic X-ray, it might be logical to think that it would reach our detector, but it's such low energy that it will be attenuated long before it ever reaches the detector. Now, thank you for submitting that question. It's a great question to get you thinking about X-ray production and X-ray interaction with matter and the subtle differences that occur at each of those levels. Now, if this sounds like a foreign concept to you and you are studying for your radiology physics exam, I've got a course that I'm going to link below here. Go check it out. The first module is free. Otherwise, I'll see you next Friday for the second edition of Physics Fridays.